be good if you can send me your slides afterwards so I can upload
Okay.
it on
Yep.
Hackday. Okay,
I'll
cool.
I'll send you the artifacts afterwards.
Yep. Okay, thank you everyone for joining. We have a big audience today. And this is our 21st session now. And starting from today, September and October, we're gonna have some guest lectures. And just to remind everyone, in case there's any newcomers, also past attendees, you should know that all the materials that we use can be found through the Hackaday project, Quantum Computing through Comics. We spend 30 minutes to an hour on topic, and we used quantum computing documentation from Microsoft and the katas as our exercises. So if you visit previous classes, the recordings are all up on Hackaday. You should be able to also follow some coding exercises. As I mentioned, starting from today, we're gonna have a series of very interesting topics from our guest lecturers. So today we have Professor Terrill Frantz talking about quantum cryptography. And later on, we'll have quantum tomography, Q-Sharp community project, Q-Trill, quantum machine learning, quantum error correction, all these great topics. So you have been coming to the class. I have taught 20 classes, and if you follow most of it, you would be able to have the background needed for these specific topics. And it would help that you took those classes because these are all very specific topics that you would need the fundamentals for. So we're very much looking forward to all the guests. We have a really great lineup here. Um, so today we have Professor Frantz. He's a professor at Harrisburg University of Science and Technology. And he also hosts several meetups, including the Philadelphia Harrisburg Quantum Computing Meetup Group and the Quantum Appalooza that he manages. He's been coming to the class and it has been a great support of quantum computing education. So today he will be talking about quantum cryptography and talk about quantum key distribution, and we'll see some examples of how Alice can send information to Bob without being eavesdropped. So we did do 2 classes on Shor's algorithms. So if you have taken those, today's class will also have some relations to that. A side note is that people have been asking about the comics that I've been drawing. So actually,
All right.
I just made that available, so you can buy it now. It's on Amazon. I have this proof copy here, so it's all printed out. You can use it as a companion book for this class. So you can watch the video and look at the comics there and take notes on the other side. So this is my proof copy, and next week I will have my author's copy. That's like what you will see on the shelf. So yeah, this is on Amazon. You can find it now in your respective Amazon stores, and I'll post the code in the chat later. So all of the information, including today's talk, will be recorded and uploaded on YouTube pretty much right away after the class. So if you miss anything, you can always go back there. Hackaday also started uploading all these classes, so with a little bit of edit. So if you can also check out their playlist. And yeah, and we're hoping to do some Q&A, and I will also be doing the drawing as Professor Frantz gives the talk. So
Yeah.
I can't guarantee that it will be in the state of publishing today, but I will use it as a note, and I hope the class here are also taking note. So drawing is my way of taking notes. That's what I'm gonna do, and I can show people at the end of the class how that looks. And then, yeah, next week we will have Professor Chris Ferry talking about quantum tomography, and we have Q-Sharp community member Prof coming the week after. So take a note at the time change next week, but then the week after we are back on normal time. That's it. So let's welcome Professor Frantz. Thank you for joining us.
Thank you, Kitty, for allowing me to not only get off of mute, but also grab control of the screen. It's an honor. And I'm shocked you remember the comment from like a week or two ago about you doing some live drawings. I don't think anybody would be paying attention to me now.
No, I won't
I'm
be showing
excited.
people while
You
you're
won't?
giving it.
Oh, well, I was hoping you had the cam on your pencil or whatever, your pen or whatever.
That's distracting.
And last thing before I get started here is my daughter started a new job and I'm looking for some wardrobe or something nice to get her. Do you have any ideas of some nice wardrobe I could get my daughter for her new job present?
Are you asking this to let me talk about my fashion brand?
Oh, I didn't think of that. Yeah, tell us about your fashion brand, please.
It's called Art by Physicists. Letting people know that this is not set up. I am surprised that Professor Frost is asking about it. But yeah, if anyone's interested, you can search kittyyoung.com and that will pop up. You'll see some interesting science-inspired designs and wearable technologies.
I'm waiting to see someone walk down New York Times Square wearing one of those.
Yes, you should should have your daughter wear it.
She's in Philadelphia, but that's close enough. Well, she goes up to New York a lot. So anyway, okay. So I'm going to try to open the share thingamajiggy. And I think you can see a screen with quantum cryptography written on it.
Yep.
All right. So I'm going to be moving around here, different modalities. So if anything gets weird, let me know. Already I lost something. Oh, there it is. All right. So what I'm going to try to do is, first of all, I've been working with classical computers for 46 years, to tell you the truth. About 20 months ago, Shor's algorithm found me when I was working in the cybersecurity space, and I haven't looked back since. Quantum is an exciting field. Classical computing gets kind of dull after a while, believe it or not. But anyway, over those years, I basically came up with, the model of, computers. Everybody thinks that computer technology is really, really difficult. And, it really is not. What it is, it's a whole lot of little ideas, tiny ideas, actually, in some cases, piled on top of each other. So it looks like it's really complicated. And that's where it gets complex. It's because it's a whole bunch of little ideas. But if you take each idea and just look at it for what it is, bit by bit over time, you'll start to understand the big picture. And I think quantum is the same thing. So here I'm going to talk about quantum cryptography, and it's really following up on page or slide or illustration number 41, which goes back to, I think, session 17 and 18 when Kitty was talking about RSA encryption, which then led to Shor's algorithm and such. So what I'd like to do, though, one of the things that happens in quantum, because there's so much here, there's a lot of hand waving going on. I mean, we've only got a few minutes each Sunday to cover a topic, and Kitty sometimes does a deep dive and then sometimes stays high level. So what I'd like to do is really kind of mix it up a little bit. And there's another, she gave an example, etc., of the RSA. But I'll mix it up a little high level, a little low level, and hopefully it floats your boat, because we've got a mixed crowd here. So first of all, when it comes to exchanging information in secret. I think of it as a 5-step process. First of all, between two parties, you need to have an agreement as to what your secrets are going to be, what your protocol is going to be, how are you going to communicate, and how are you going to communicate in secret. Then there's a next step, because there's lots of ways that we can communicate in secret, from Caesar's ciphers, as I think Kitty may have mentioned, which goes back hundreds of years, to things being developed today, and NIST is working on post-quantum cryptography. So there's quite a variety of techniques for sharing information in secret between two and sometimes more parties. The second thing is, once you get an agreement, generally, and this is a still generalization, is the parties need to develop some sort of key, some sort of secret compass or what have you, some sort of secret between them. And then once those keys are generated, they need to be distributed. They need to be sent from Alice to Bob and Bob to Alice and so on. And then you have the steps of encryption and decryption. And let me just bring this home a little bit. Most of you probably don't realize that when you go to a website nowadays, I think it's like 70+% of websites now use HTTPS. It's up there. Well, I guess you'll normally see it as a little lock up on your browser, up near the URL. And that is HTTP with a security protocol, agreed security protocol called SSL TLS. And this is really when you first reach a website, there's this handshaking process going on, and it goes on very, very quickly, thank goodness. You don't even realize it, but your laptop sends a hello message to the website, and with that hello message, your laptop gives a list of protocols that your laptop is prepared to use for secret information exchange. And the website on the other side, on the server side, takes a look at the list that your client can communicate with and selects one of those protocols, and then sends back okay, here's the deal. This is the protocol we'll use, and that's over here in this part here. And so there's this dialogue that goes on very quickly, because there's a whole bunch of different ways to encrypt your data and keep it secret. And so this happens very, very quickly every time you go to effectively a new web page. Another bit of background is cryptography has two basic food groups, if you will. One is where you have a symmetric key where Alice and Bob basically use the same key. And then there's asymmetric, which is where there's a different key for the encryption and decryption, etc. And so typically, Caesar back in the day used what's called the Caesar cipher, and that's where they just shifted characters in the alphabet. So if you had ABC, they would shift it by, let's say, 3 or 4 letters, and ABC would come out as XYZ, etc. I think most of you are fairly familiar with that. So let me get to a little bit of detail here. Let's step back a bit, and I'll pull out the magic whiteboard because I want to compete with Kitty on some drawings here, so I'm going to try. So let's get down into the real nitty-gritty of what goes on. So what if I wanted to send the message, the word comic, from Alice to Bob? Well, let's remove some of that magic. First of all, we don't really send characters, COM and all that. And I don't like to take shortcuts when doing stuff like this, so I'm going to show you exactly what I do, even looking up the websites. So what the word comic really looks like, now let's stick this over here. It's over here. When we send it through the internet, it's like the 3-planet problem here. I got 3 things going on. There we go. All right. So, and we'll say that that's a little c, lowercase c. So over here, this is really what gets transferred over the internet. We call it data in transit. So the C becomes 1 or 0, 1, 1, 0, 0, 0, 1, 1, and that's a C. And the O, I'll look up an O, becomes a, let me see, 0, 1, 1, 0, oh, that's convenient, 1, 1, 1, 1. All right. So that's really the first abstraction. A lot of people think that the letter C and O actually go through the airwaves, and no, that's not exactly right. It's a series of zeros and ones, ons and off, bits and bytes, 3 volts and 5 volts, etc. So this is, and I'll just use C and O, but I'll just boil it down to just use C because I don't want to be drawing all day. So if I wanted to send it a C from Alice to Bob, this is what would get sent. 0, 1, 0, 0, 1, 1. Now, clearly, if I sent that through the internet, Eve would be able to decipher that. She would be able to say, oh, well, that's a C because I can just look it up in this table. So what if I took this code here and put a key against it? I processed it with a key, and therefore, let me see. So 1, 1, 0. What would actually be sent over the wires would be this 0, 1, 1, 0, 1, 1, 0, 1. And if I look this up over here, 0, 1, 1, 0, 1, 1, 0, 1, it would be a small m. So now the cool thing is, if I take this same key, this guy up here, and did the same, process it on again, and I'll explain the process in a second. When I decrypt with the same key, then I get the C again. So come back over here. And it's this guy right here. So what algorithm, what rules did I use here? And this is just an example. I used what's called XOR, exclusive OR. And XOR is where if you have two inputs, if so, the result would be a 1 if there is only one in A or B. So if I had 0 and 0, the result in an exclusive OR would be a 0. If I had a 1 and a 0 with exclusive OR, I would have 1, which means that there's only one 1. If it was 0 and 1, I would end up with a 1. If it was 1 and 1, what would you get? The result would be 0, because the rule is if there's only one in the pair, then the result is a 1. If there's no ones in the pair, the result is a 0, and if there's both of them are 1, then it's a 0. So what I basically did was use XOR here. But so the key here is you can see, hopefully, at the minute detail of how I can take a message, in this case, just a single character C, apply a key to it with some rule.
Cryptography.
I can get a different character from that, M in this case, and I use the same key, this is identical here, with the same rule. Again, then I get the original message. All right, now that's as simple as it gets. And that's all that's really going on. So the key here is this guy right here, right? Literally the key. So if I just look at the key, and it doesn't matter what I have now because I'm not going to, I'll get away from that example. 0 0 0 0 1 1 1 0. And I could give any key here and do this process and it will work. So in quantum cryptography, one of the primary use cases of quantum mechanics and all the quantum features is sharing this key between Alice and Bob, because remember, one of the steps is the key distribution. And that's really one of the main use cases for quantum. And so how does Alice and Bob, how can they share this key? Well, in quantum, we have a real important feature called the no cloning. I guess it's a theorem where we are going to take advantage of that. And this means you basically can't copy information. So if Alice is here and Bob is here and Eve is here, in classical, if Alice sends a 0 to Bob and Eve takes it, Eve can copy the 0, stick it over here, and then pass on the 0 to Bob, and Bob would never know what happened. Well, with the no cloning theorem, if Alice sends a 0, Eve intercepts that 0, Eve looks at that. Eve basically will try to copy it. So Eve will know it's a 0, but the thing is Eve cannot copy it. And so what Eve has to do is randomly send a 0 or 1 to Bob. Eve can't do like in the classical case with the classical computing paradigm, she can't make a copy of it. So if she takes what Alice sent, sure, she knows that it's a 0, but what she has to pass on to Bob is either a 0 or a 1. She can't just copy it. And that is the essence of what quantum key distribution takes advantage of. Eve cannot simply copy this state here and send it to Bob. Now you'd say to yourself, okay, well, it doesn't seem too difficult to do that. I mean, if she knows if he or she knows if Eve knows it's a 0, well, then just send a 0 to Bob. Well, it's not quite that straightforward. So any questions or anything like that at this point? Comments before I get into the fun stuff? It's okay to interrupt at any time. All right. So let's step back for a second. Imagine I had a machine. Let's just call it A. I better not do that because you might get it confused with Alice. Let's just call it little a. So it's a machine. And if I put in a value into A will repeat that value like that. If I put in a 1 to A will simply do that. Now let's say I had another machine, B, and I put in a 0 there, and out comes a 0 with a B, and I put in a 1 here. Oops, it's a B, little b, and I get a 1 with a little b. These are little b's here. Now, however, if I have A here and I put in a 0B, A will 50% of the time spit out a 0A, and 50% of the time a 1A, and ditto would B. So let me just finish A. So if I put in a 1B here into little a, into machine A, 50% of the time it'll come out of 0A, and 50% of the time it'll come out of 1B, 1A. And so B is essentially the same thing. So essentially, if you put in like a raw value in here, it'll spit it out with the A on it. But if you put in a value from the other machine, and the same holds true with B, from the other machine, it can't quite read it properly. So what it will do is it'll randomly say it's a 0 or randomly say it's a 1. Right? And B's got the same issue. 0A. And so on. Whoops. That's a 1A. See, this is why we should be watching Kitty draw. All right. So let's say Alice has wants to send this key. What is it? 0001110. 0001110. Alice wants to send this to Bob. So what Alice does, she randomly chooses between machine A and B. So let's say she'll do A here, B here, A, B, A, B, just randomly. So she'll kick out here. Let me see how to draw this. So we got a 0A followed by a 0B followed by a 0A followed by a, I'm doing this backwards, right? Because she'll send these out first. And then a 0A and then a 1B, a 1A, a 1A, and a 0B. So now Bob, I guess I can go to full screen here. So she sends this set of values to Bob, and Bob's over here. Let's say Bob decides, well, I'm going to read these strings using machine A, then I'm going to use machine B, and then I'll use A, and then A, and then A, and then B, and then A, and then, I don't know, B. Because remember, Bob and Alice aren't talking. They're only communicating with this stuff here. So Bob uses A. Let me see, what's the best way to do this? So if Bob uses A and sees that, so he'll get a 0, right? Here he's going to use machine B for the next one. And so he'll correctly get a 0. Nice. Here he uses A. Oh, wow. That was an accident. Oh, well. So he correctly gets the first 4 bits correct. And then here he has a 1B coming off using machine A. Now remember over here, a 1B with machine A means there's a 50% chance he'll get a 1A or a 0. So let's say he gets a 1. And here, let's say he's getting 1A, machine B. All right, well, he's got a 50-50 chance. So let's say here he gets a 0. Gets a 1A here, reads it with machine A randomly. So that's a correct 1. And then here he gets a 0B and a correctly because it's the same machine. And he doesn't know what machine this came from. He gets that right there. So you see, the string matches, but right here, and he doesn't know what Alice sent. So, you know, he doesn't know what machine Alice's numbers came from. He knows the numbers, but not what machine they came from. So what Bob then does, sends back the list of machines he used. So he sends A, B, A, B, A, B. He sends this list back to Alice. Alice compares it to her list. So Alice, remember, she knows what she sent. She knows what Bob, machines Bob used. So she knows that Bob is probably wrong. Let me see. Let me get this right. A, B. She knows that Bob is going to be correct with these values, but these two, he's got a 50% chance of being incorrect with each one of those. All right, so Alice sends back, okay, Bob, you are incorrect on 1, 2, 3, 4, number 5 and number 6. So Bob then says, all right, well, these I'm going to throw away. And therefore, Bob knows that these values are correct. So what if Eve's in the picture? If Eve was in here, this is where the drawing gets kind of difficult. Ooh, purple. Goodness, let me see here. Oh, here we go. I need to take some lessons from Kitty here on, there we go. Okay, so here's Eve. Now keep in mind, if Eve intercepted this, the A0 or 0A, 0B, and so on, she only has, she's going to select, let's say B, A, just randomly, I'm going to just keep it simple. And so when she gets the 0A, she's got a 50% chance of it being right or not. So she has to say, okay, well, that's a 0, but she doesn't know that. And here, that's a 50% chance of being a 1. Now here, she'll be correct, but these have a 50% chance of being incorrect. Here, she measured with the same one. Here, she measured with the same one, so that's correct. Here, she, so these are correct. This one's wrong here, possibly. It's a 50% chance of being wrong, remember? And then A, so here, that's a 50% chance of being wrong. So now Eve needs to send, to make sure Bob gets something. What does she send? She sends a 0, 1, 1, 0, 1, 1, 1, 0. Now remember what Bob does. So Bob takes a look at this, and these should be A, B, A, B, A, B, because Eve doesn't know what Alice sent. So Bob now takes this, all right, that's an A, so that's a 0, that's correct. Got a B, that one's it's the same, that one's the same here. So it's a 0B, Bob's using machine A, so there's a 50% chance that it's correct. Here's a 1, and from machine A, I don't know if you can see it, I wrote pretty small here. So machine B, that's an A, so there's a 50% chance. That's correct. This one matches, and 0. So now, keep in mind, Alice and Bob don't know that Eve exists. Bob sends back the string of, let me see where are we. So he sends back the string here that he used, and Alice takes his values, thinking that these are correct here, and what she knows that this would be a 1 and this one would be a 1. Bob sends part of his solution also. In fact, I'll send Eve's version. When Alice sees this mistake here, they have now discovered that Eve is listening. So in trying to keep this short, boy, time flies when you're having a great time. When Eve is listening to this exchange, Eve introduces error that goes beyond the error that Alice and Bob would expect. So Alice would expect Bob to be wrong, if you do the math, to be wrong 75% of the time. If Eve's involved, or to be correct 75% of the time, because of this translation going on here. If this value becomes less than 75%, let's say 63%, Alice will know instantly that Bob and Alice and Bob's conversation is being watched by Eve, because the correct rate is below what it should be, which is 75%, give or take a few percentage points. And this is not over, 8 qubits here. This is over, 1,000 qubits, let's say. So, the difference will be noticed. So, in short, that's really what quantum key distribution is all about. Is when they reconcile, they think of it as these two machines that process the data, and when they reconcile, if the error rate is greater than expected, then they know Eve is listening. Now, let me take this from the notion of machines to the physics. And this is really Kitty's department more than mine. But what's being exchanged here are protons. And protons, coolly enough, very coolly enough, let me see, I think I got something in the slide here. Might be good.
I mean, if you need
protons,
to use the powder, I'll take one. Okay.
So protons essentially have two ways of what are called two bases. They have a horizontal and vertical basis, and they have a left and right basis, or a diagonal basis. This is called rectilinear basis, and this is called a diagonal basis. So you could think of these two bases as the machine A and machine B. And if you have a proton coming along, it will be in a wave form that is both horizontal and vertical, and diagonal, left and right. mixed.
Photon, not proton.
Oops, thank you. See, I told you this is not my neighborhood here. I got to write it down so I remember. Proton, right? All right. I'll take silence is good. Anyway,
Photon.
so
Photon.
photon. See?
Photon. Like photograph.
Yeah, photon. Yeah. All right. See, now I'm out of my range here. So I recognize the voice. So it's just like a pair of sunglasses that are called polarized sunglasses, so that if I had a filter, a polarizing filter here, this will block the vertical waves, but allow the horizontal to, it'll block the horizontal, right? But let the vertical waves come through. So you could think of this as, let's say, machine A again, and it's either vertical or horizontal, and that could be either a 1 or 0. Now, if I had a different polarization filter or polarizing filter, and it was on the diagonal, think of that as machine B, and it will let only left or right one of these through, which is either the 0 or 1. So that is essentially how quantum key distribution works. And what's interesting here is that if you go back to good old, plain old cryptography, when you have a message and you have a keypad or a key value that's used once only. So if I had this as my key, and I use it once, according to one of the gurus, Claude Shannon, is that this is impossible to beat. And so using this quantum key distribution technique, you have a one-time pad that matches the data. So let's say you had 1,000 bytes or 1,000 bits of data. You would have a quantum key of 1,000 bits, qubits paired up with that. And those qubits are this key here, just as I described using the two machines or the photons. So I think that's enough for now. That should give you a basis for, there's plenty of videos out there, plenty of writing about what I described is called BB84. So it's my belief that with what I discussed here, you should be able to watch a BB84 video and follow along. They typically start with the physics, but what I decided to try to do here is start with the logic behind it and then get into the physics, which is where protons, photons, I can get that all mixed up. That's really, I can't believe it's already 3:20. I could go on and on, But that's basically the gist of what's called BB84. Charles Bennett, by the way, is still at IBM, and he has a few talks out there that'd be well worth watching. There's also a revised version called I think it's 92, where instead of using both bases, that's these guys here, or both machines, it's a technique that actually just utilizes one of the machines, either the horizontal, vertical, the rectilinear, or the diagonal bases here, or filter. Let me just end with this slide here. One way to get your head around this, finally, and I have this stuff at the office at the campus, but I haven't been there in 6 months, so I just have to use some pictures here. Imagine I have two pairs of sunglasses, one here, and I put them on top of one another, and I turn them at a diagonal, make them perpendicular to one another. What I'll see is zero light here. Okay, it'll block all the light. So this is think of it as a filter going like this on the bottom, and then the one on the top goes like this. So what do you get? You get no light. Now imagine I take a third filter. Let's call the third filter Eve, and I insert it between these two filters here. You'll see I'll get some light. So this is a physical real-world example of this technique in operation with a man in the middle here affecting the outcome. I should not, if Eve was not there, I would have complete darkness. But if I take a polarizing filter and stick it between these two filters here, these two pairs of sunglasses, actually I'll have, and this is between, this is not on top or behind it, it's in between these two. I'll actually have more light coming out than if I only had the two. And that's it from here. Way over time, as usual. Any questions, comments? I tried to compete with Kitty on the drawing. I don't know if I even came close.
Not really compete. Thank you for doing this. Your drawing made it much easier. I mean, yeah, it's pretty much the same as what you did. I have to tidy it up, and I can probably show it, put it into a 1-pager or 2-pagers next week.
Cool.
Thank
Any
you so
comments? You're welcome. I'm way over time. Apologize for that, because I know it's nice when it's short on Sundays.
Yeah, I think we can have a fight about protons versus photons.
I don't know the difference yet.
Oh, there's two different fundamental particles. But yeah, in the communication, in this case, usually people have been using photons as the medium, as the polarization carrier. However, it doesn't mean that protons cannot have polarizations. So the reason that we're not using protons for communication is not because of fundamental physics that forbids it. It's just an engineering problem, and it's also convention. So if you do want to use protons for communication, you can probably try that too.
I'm a software guy. I came up through business school. I'll do whatever you tell me to do, Kitty.
I'll be interested to see any proton.
It's practically impractical to use a proton particle as a channel, because the amount of energy required, repeaters and all that. There's a reason why over the years it has taken, for photons. Photon is a particle of light. Very difficult to observe a photon, but there's a reason why there's a photonic channel, i.e. optical channel, and not a protonic channel. So I think from a computing standpoint, this is a tried and tested thing. Proton channel does not work. Yes, if you're doing a some kind of hadron collider experimentation where you're actually bouncing protons and measuring them speed and observing particle collisions, a different story altogether. but from a communication perspective, it does not work.
Why does it not work? Is there any physical rule, physical law that's
Photons have spin 1 or spin minus 1, so they can be equated with 1s and 0s, whereas
Every particle has it.
whereas protons are plus half and minus half, and it wouldn't be directly translatable to 1s and 0s, I don't believe.
But you can map it. You can always come up with an algorithm that maps to whatever spin or polarization that is allowed.
Yeah. By the way,
what I'm saying is an engineering problem, is not fundamental physics that doesn't allow that.
That is you, Michael.
Yeah, it is. Hey, I know you recognize me, but Terrill, who is the IBM scientist who came up with the BB84 encryption?
Charles Bennett.
And is he still at the IBM Research Lab?
Yeah, he just gave a really nice video on either I think it was their Friday session about 3 or 4 weeks ago.
Yeah, I used to work at IBM Research in Yorktown, New York, but I probably predate him. I mean, I go back a couple of decades.
I would imagine he goes back pretty far too.
Yeah, actually, the name sounds familiar. Yeah.
Yeah, look him up. There's a really nice video.
Yeah.
Get in touch with him too, Don't hurt. People in quantum are approachable. I had some emails yesterday with some really big names. You would be surprised how receptive people are.
I hope he doesn't recognize my New York accent as you did.
I know you from the Brooklyn sessions.
Yeah, I know. I'm
Anyway.
too loud. I'm too loud. I'm too close to my microphone.
I had to mute you.
Oh.
Thanks, Terrill.
Pleasure.
Thank you so much for the lecture.
Okay.
It's a great meetup. Great to talk about this. Hopefully it was helpful for the audience here.
Yeah, the key is watch a few other videos, because this always gets, no two descriptions of this are the same. And like a lot of things in quantum, just like when Kitty talks about things, I go visit other videos because everybody has to leave something out. And so, but you put them all together, you've got a pretty good story going.
Great. Thank you so much.
Right.
See you next week.
Thank you.
All right.
This is
Bye,
awesome.
everybody.
All right.
Bye.
See you
Have a
next
good day.
time.
Safe.
Thank you.